This is PowerPoint 6B. In 6A, we sort of finished up by talking about the various kinds of precipitation: rain, drizzle, virga, snow, snow pellets, snow grains, sleet, freezing rain, and then we ended up with hail. I hope you took the opportunity to watch that YouTube hyperlink on the PowerPoint. If you didn't, take the time to go back and look at that as you're studying Chapter 6. It shows a tremendous hailstorm in Oklahoma, suburban Oklahoma City, in May of 2010, and you're not going to believe the size of those hailstones as they pound into that swimming pool. So I'm going to tell you right now, if you didn't watch that, at least for entertainment value, go back and watch that. I think you'll find it amazing and amusing simultaneously. All right, figure 6.26 from your book gives you a generalized picture of annual average global precipitation. The scale is both in inches and centimeters. Gives you kind of an idea. Obviously, the places that are wettest in the world, the blue and purple places, are places where rising air or low pressure dominates. In places that are driest in the world is where sinking air or high pressure dominates. So the driest areas, of course, are the poles of the Earth because they're essentially frozen deserts, and then the mid-latitude subtropical deserts, like the desert southwest of the U.S., and you can see that big swath of dryness across the north part of Africa, which is, of course, the Sahara. Here are some global precipitation extremes. I'm not going to go into great detail on these. You can certainly study them in your textbook. Greatest annual average rainfall in some places, least amount of average annual rainfall, driest deserts, wettest places on Earth, and so on. So you can study this on your own. It's figure 6.29 from your textbook. We talked about the influence of mountains, especially we talked about that in Chapter 5 with lifting of air by topography and the rain shadow effect, with the windward side of a mountain range being wetter than the leeward side. In the continental United States, the 48 contiguous states, nowhere is this more dramatic than in the Olympic Mountains of northwest Washington. This is just astounding. Where in Olympic National Park, a place called the Haw Rainforest averages 134 inches of rain a year. Okay, get that. Just make a note of that. Averages 134 inches of rain a year. Moss would grow on you, right? Okay. Then, just not too terribly far away, on the leeward or dry side of the mountain with descending parcels of air, is Port Townsend, Washington, which has an average annual rainfall total of 18.4 inches of rain a year. So it's really astounding that in a short distance of not very many miles, you have 134 inches of rain annually on one side of the Olympics and only 18 inches of rain on the other side of the Olympics, on the leeward side. This is a nice cross-section that I really like to show, figure 6.29, which shows you the effect of topography on average annual precipitation across the western U.S. This is California and Nevada. Cross-section essentially from Santa Cruz all the way to Tonopah, Nevada. And the purple down below shows you average annual rainfall in inches and centimeters. Here in the San Joaquin Valley, you see that there's a rain shadow on the west side. If you looked at the statistics, I happen to know them in my head. Coalinga gets about 9 inches of rain a year. Fresno gets about 11.5. And then when you get to North Fork, it's about 30 inches of rain a year. So you really can see how lifting by topography or sinking by topography has a lot to do with a lot of rainfall or the lack thereof, depending on whether you're on the windward side of the mountain or the leeward side of the mountain. All right, where it's wet and where it's dry. The rainiest places in the world tend to be located on the windward side of mountains. Snowfalls are going to be heavier where cool, moist air rises along the windward slopes of mountains. When I say rainiest, I also mean areas of the most precipitation, because ultimately snow is kind of dicey because snow can have a high water content or a low water content. So it's a little bit of a misnomer to measure snow depths, because snow depths can have different water content even if the depth is the same in one place or the other. So the wettest regions of the world tend to be on the windward sides of mountains. The driest regions of the world tend to be in the poles, as I told you before. The leeward side of mountains, that's the rain shadow, and the belt of subtropical high pressure, which is sinking air, which is located between about 15 degrees and 30 degrees latitude on either side of the equator. We'll talk a great deal more about the global circulation of air in a future chapter. This table shows you the wettest cities in the United States, of course, including Alaska and Hawaii. And there you go. There's a place in the southeastern part of Alaska that gets 160 inches of rain a year. You're not going to find any of those places in California. And they do this two ways. They show you the average annual precipitation, and then they also show you the average number of days each year on which precipitation falls. So there's two ways of looking at the wettest cities in the United States. Now here are the driest cities in the United States based on column A, average annual precipitation, and column B, the average number of days each year with measurable precipitation. So if you look at this list, you see the valley city of Bakersfield on the left only gets 6.5 inches of rain a year. Fresno gets 11.5. We get almost twice as much as Bakersfield does, even though we're only 110 miles apart. Now, look at the column B, average number of days each year with measurable precipitation is what that is. And check out Fresno. We only have measurable rain on 45 days a year. So let me tell you something. Rain around here is an anomaly. When it happens, it's a big, big deal. Look at Bakersfield. Measurable rain on only 37 days annually. Keeping in mind, of course, that there are 365 days in a year. Many of those dry places are right here in California. Now, the other extreme, too much rain, floods and flash floods. What is a flash flood? Those are waters that usually rise very, very rapidly with little or no warning when thunderstorms stall or move very slowly, causing heavy rain over a relatively small area, very rapid accumulation of rain. There are some very, very famous flash floods in the United States. Most famously, July 31st, 1976, the Big Thompson Canyon of Colorado in the Rockies. Your book has a special interest box about that flood, I believe. Now, more general flooding occurs primarily in the spring when heavy rain and melting snow cause rivers to overflow their banks and when excessive repetitive rains hit a wide region. There's a little bit more warning on that kind of flooding because you have maybe days to get out of the way. But flash flooding comes on so suddenly because the soil is not able to absorb the high rate of rainfall that occurs with a flash flood. Let's go back to general floods for just a minute. June 2006 in New England, that was one. June to July 1993 in the central United States, that is often referred to as the Great Flood of 1993. Now, in those cases, the same areas were hit day after day after day by repeated thunderstorms. This is an effect called training. It's like hooking cars onto a train, one after the other, where, of course, the additional cars on the train go over the same track. This is what happened in these areas. In New England in June of 2006, and also the central U.S. in June and July of 1993, the Great Flood. In the winter and spring, late winter and spring, ice jam flooding can occur, especially in areas in the northern plains where maybe a river has frozen, and then the river starts to flow because the ice melts. But large chunks of ice get caught in a weir or in a bridge, and that dams up the water. So that causes a real big problem. Grand Forks, North Dakota, I think, is a place where this is very famous for. Dissipating hurricanes and tropical cyclones can cause widespread inland flooding. Notably, Tropical Storm Allison in June of 2001, which dumped 20 inches of rain on Houston, Texas in 12 hours. Now think about that for a minute. If Fresno got 20 inches of rain in 12 hours, it'd be an absolute disaster here for a long time to come, cleaning up after that. We get 11.5 inches of rain in a year. They got 20 inches of rain in 12 hours. So put that in perspective. Graphic on the left shows you the area in blue covered by the Great Flood of June and July of 1993. And this also shows you the capital city of Missouri on the right, Jefferson City, Missouri, during that Great Flood of 1993. So how do we know where rain is reaching the ground and how much rain is coming? And it's kind of a short-term phenomenon. And this is where the tool of Doppler radar comes into play with the National Weather Service. It's a very important tool. The National Weather Service has a network of radars around the United States. There are about 160 of them. About 120 of them are associated with National Weather Service offices, and the other 40 are associated with the military installations. Radar is actually a word that's made up. It's an acronym for radio detection and ranging. Here's how it works. A radio transmitter sends out a short, powerful microwave pulse. When that pulse hits an object, a target, i.e. like a raindrop or a hailstone or a snowflake, it scatters a fraction of that energy back to a receiver at the weather station. That received return pulse, which is called an echo, is analyzed by special computer programs called algorithms that meteorologists and scientists review to determine the distance that the precipitation is away from the radar, how intense a rate that the precipitation is falling, and the nature of that precipitation. Is it rain? Is it hail? Is it snow? Is it drizzle? And so on. So that's how Doppler radar measures precipitation. So Doppler radar essentially analyzes the movement of particles in the air, precipitation particles when there are clouds, and other particles in clear air. For instance, I've been told by the folks at the National Weather Service in Hanford that once the sun rises and the migratory birds start to fly in the morning, that they can actually see those movements of migrating flocks of birds on their radar in clear air. The radars employed by the National Weather Service and the military across the U.S. for weather purposes are called WSR-88D, which means Weather Surveillance Radar, developed in 1988, and it's a Doppler-type radar. It uses a principle called the Doppler shift or Doppler effect, which was discovered by Austrian physicist Christian Johann Doppler in 1842. It's based on the change of frequency in waves that occurs when either the emitter or transmitter of the wave is moving toward or away from you. Here's a perfect example. If you're walking down Shaw Avenue here in front of campus, and a friend sees you walking and they honk their horn because they want you to wave at them, and they lay on their horn and it's going, meow. The sound of the horn sounds differently, doesn't it, than when the car was approaching you with your friends in it honking the horn. That's the Doppler effect. So that's something I think you can sort of will actually experience in reality. Here are two products from Doppler radar. The one on the left shows what we call base reflectivity. That's where rain is reaching the ground, falling from the clouds, and the green might mean light precipitation, the blue might mean precipitation not reaching the ground, and the yellow means moderate precipitation. Then there's another product. There are many products we can get from Doppler radar, but these are just two. The one on the right, figure 6b, shows the past 1 hour precipitation totals estimated by the radar, actually estimating how much precipitation reached the ground at particular points within the range of the radar. What's the range of these radars? About 120 miles or so. Now, we've talked a lot about flooding and a whole lot of rain. Let's talk about drought. That's defined as a period of abnormally dry weather that produces a number of negative economic and social consequences. Now, a drought is not a dry spell. Heck, we have dry spells in California every summer. But in order to quantify long-term drought, there was a meteorologist by the name of Wayne Palmer, who was with the U.S. Weather Bureau in the 1960s, which is now called the National Weather Service, who developed a special index, which is called the Palmer Drought Severity Index. It takes into account the average temperature and precipitation expected on a regional basis and the comparison to actual temperatures and precipitation observed over several months in that same area. There is also something called a Palmer Hydrological Drought Index, a PDHI, as opposed to the PDSI, which takes into account groundwater reserves and reservoir levels. Now, if you click on this hyperlink, it will take you to the current Palmer Drought Index. The one you see on your screen here is from November 2012. Speaking of droughts, here are some notable ones. In the marginal area south of the Sahara Desert called the Sahel, in Africa, they're in perpetual drought that causes food shortages and starvation. Of course, the Dust Bowl of the central United States is famous. You may have watched the Ken Burns PBS documentary called The Dust Bowl, which aired a few months ago. It's quite compelling. There have been droughts in California in the 1970s, most recently 2007 to 2009 as well. Driest cities in the United States, guess what? Fresno is on there, Bakersfield is on there, Reno is on there, and so on. So you can see a lot of western states. Once again, it's worth repeating this graphic. So there you go. We are now ending Chapter 6, Part B PowerPoint. I hope you found interesting and instructive. extremes in precipitation, wet and dry, in this PowerPoint.